Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the continued part of the lecture 17 on the course under SwayamPrabha, the course title Maritime Structures, Types, Construction, Pre-Service Analysis and Design, offered by Department of Maritime Engineering at IIT Gandhinagar. In this lecture number 17, we are going to discuss about analysis and design of beams curved in elevation. We call curved beams. So, we are now looking at beams which are curved in elevation. What we slate as curved beams. The classical example of this could be a crane hook. Okay. So, a classical example could be a crane hook. So, now we are looking at how to analyze and design a crane hook or for a load suspended by the hook or lifted by the hook, what would be the stresses developed in the hook? Friends, the conventional theory of flexure useful to estimate the bending stresses will not be helpful here, because the cross section may be of a regular shape, but the elevation is a curved profile. Okay, it is a curved profile. So, how to handle this? Curved beams can be classified in two forms. Let us say two types. One, curved beams with small initial curvature, curved beams with large initial curvature. Now, how do we classify this? In simple terms, when the initial radius of curvature to the depth of the section, when this ratio is greater than 10, we call this beam as beam with small curvature. Okay. On the other hand, if the ratio is lesser than 10, then we call that beam as a curved beam with large initial curvature. Let us be very clear, large initial curvature. So, I can classify beams into two forms like this. Now, we look at bending of curved beams with small initial curvature. Let us look at the picture of this beam with small initial curvature. So, pay attention to this figure. The beam is the profile which I am now drawing on the board. This is the cross section depth of the beam. Okay. This is the overall depth of the beam. So, this is the overall depth of the beam. The beam has got some center of curvature, right? Because the beam is curved, there is an elevation, not in plan, in front of you. The beam is curved and I take a segment A, B and C, D intersecting at the center, and I call the segmental intersection of this ABCD as D phi. So, this is D phi, okay, D phi. Now, when the beam will bend, when the beam is subjected to a bending moment M, this curvature will follow this profile, correct? When the beam is bent by a moment M, it will have this curvature. So, let us have some nomenclature of this as follows. Let R, okay, be the initial curvature. R is here. So, R is measured to a specific layer which is indicated here. Okay. This layer is measured from the center. and I call that as radius of curvature. Okay, and that axis is the centroidal axis. Okay, so R is the initial curvature of the centroidal axis as shown in the figure. Okay, then let d phi be the angle subtended at the center of curvature by the element ABCD. Okay, we have seen an element, no? AB is one frame of the element, CD is another frame of an element. These subtend an angle at the center. I call that angle as d phi. Okay. Now, when I apply the moment, now the beam is bending, and the beam is now going to bend in a new form which I am drawing here. So, let us draw the figure here. So, let me draw the beam. Just mark the center. Okay. Let us take two segments. Marked as, let us say, A, B, C and D, measure on two extreme surfaces extending an angle d phi at the center of curvature C. Now, this cross section will have a layer, okay, will have a layer. I am marking that layer, and I call that radius as R, and this layer is the centroidal layer. Okay. Now, when I apply a moment, the curvature changes. When I keep on applying moment, the curvature keeps on changing. So, there will be a stage when I will get a new curvature as I am marking now. So, let me take a new layer. PQ, a new layer PQ at a distance y from the centroidal layer. Okay. From the centroidal. Remember friends, the figure is very important because there has got a lot of nomenclature Please follow the figure. I am redrawing it carefully for the sake of you, line by line, so that you follow the figure carefully. So, I take a new layer y and a distance y from the centroidal axis. Okay. Now, since I have applied the bending, it has now taken a new curvature. Let us call that new curvature as r dash, okay, and the new center as o dash, and the new subtended angle as d phi dash. Okay. So, initially it was d phi, now it has become d phi dash. Initially it was o, it has become o dash. Initially it was r, it has now become r dash. You will notice that the fiber remains unchanged, and I am marking it here. Okay. Let us slightly, so this is unchanged. Okay. This point is unchanged. There is no change in length in this fiber before and after applying bending, correct? The figure shows that. So, now let me write r is already expressed, d phi is already expressed, see here, r is already done, d phi is already done. Now, I write r prime. R prime is the new radius of curvature of the beam after bending or after m is applied. Okay. Please note that an important statement is r prime will be lesser than r, is it not? How this can happen? This can happen only when the applied moment m tends to close the curvature. I am applying moment in such a manner, okay, the curvature is getting closed. Okay. For example, I have a straight rod, apply a moment, it becomes curved. Further moment, it becomes further curved. Further moment, it becomes further curved. So, from a straight bar, it has become closed. So, moment is applied in such a manner, that the curvature is getting closed. Okay. This is positive for me. Therefore, friends, d phi prime will be now the new angle subtended by the element after deformation, correct. I have taken an element and that subtends an angle d phi prime at the center after deformation. Okay. Now, I take a fiber at a distance y from the neutral axis. Okay. Why I am calling this as neutral axis? Why I am calling this as neutral layer? Because the layer has no change in length, right. Before curvature and after curvature, the length of the layer remains same. So, I can call this layer as neutral layer and measure the new fiber PQ from that layer, correct. I repeat again, this layer before and after applying bending is not changing, right. You can see this point is same. So, I measure a new fiber from that layer, call that as y, right. So, now I can say let us consider y be the distance the fiber or of a fiber from the neutral axis. Okay. With this data, now I can say what is the original length of the fiber? what is the original length of the fiber? Let us see. Can you just tell me what is the original length of the fiber? Can I say the original length of the fiber is r plus y of d phi? R plus y of d phi. Can I say the original length of the fiber? So, I am writing it here. It is r plus y of d phi. When I apply moment, after applying m, the length changes, is it not? So, the new length of the fiber after applying m is given by, can I say this is r dash plus y of d phi prime? See the figure? The new length of the fiber after apply m is r dash plus y of d phi. Can I say that? D phi prime, right? Now, when I know these two values, I can now compute the change in length of the fiber. Which will be the new length of the fiber minus old length of the fiber. So, if I divide this by original length of the fiber, will I get strain? So, I can now say the strain epsilon is change in length by original length, which is r dash plus y d phi prime minus r plus y d phi divided by r plus y d phi. Can I say that? Call this is equation number 1. Original length, new length minus old length by old length, okay. That is change in length, and original length is this. So, the ratio of these two as per the conventional mechanics is the strain. Having said this, we know that the length of the fiber at neutral axis remains unchanged. We can now say that ds is r dash d phi dash is as same as r d phi, because there is no change in length, right. See the figure here. At the neutral axis, whether you say this length before or after bending, it is unchanged, right. The point is same. So, that is what I am saying, I am calling that as ds. Equation 2. Now, what I do? I substitute equation 2 in equation 1. Equation 1 is here. So, please do that and see what happens. Strain now becomes y into d phi prime minus d phi by r plus y of d phi. Am I right? We simplify. Okay. Because r d phi prime and r d phi are same. So, in this equation I can expand this if you want. So, epsilon originally was r dash d phi dash plus y d phi dash minus r d phi minus y d phi divided by r plus y d phi. We already said that this is same So, I can now say r dash d phi dash and r d phi are same. So, taking y common, I wrote this and I retain this as it is, and that is okay, right. So, equation number 3. Any confusion in equation number 3? Is it okay? So, please do derivation in parallel with me, so you will understand what I am saying, right. I am going step by step and I am not hurrying it up. Okay. Now, in equation 3, y may be neglected in comparison to r, because r is very large. Okay. R is very large compared to y. Y is a segmental length in the depth of the beam, whereas y is the initial radius of curvature of the beam, is very large compared to y. So, I can now say in this equation 3, let me write down the equation again. In equation 3, which is epsilon equals y d phi prime minus d phi by r plus y d phi, we can say y is much lesser than r. Therefore, E now becomes y times of d phi prime minus d phi by r d phi, because you know y is very small, I neglect that. Call equation number 4. So, now I want to use equation 2 and simplify 4. So, using equation 2, we try to simplify 4. What is equation 2? Equation 2 talks about the curved length of the fiber at neutral axis, right. So, let us use this equation and simplify this equation, see what happens. Please do it, I will also do it here. So, epsilon now becomes y times of d phi times by ds minus d phi by ds. Is it okay? Is it okay? Because I am using this equation to simplify this. So, wherever I have r d phi prime and r d phi, I am using ds. Okay. So, I have written this way. So, now I can simplify this further as which is equal to y times of 1 by r prime minus 1 by r, which I call equation number 5. So, friends, we know strain is stress by E. Okay. So, hence y times of 1 by r prime minus 1 by r should be equal to stress by E. So, can you now write stress by y is E times of 1 by r prime minus 1 by r, equation number 6. So, conventional bending theory or theory of flexure will give you stress by y 1 by r m by I, whereas in our case stress by y is E times of 1 by r prime minus r, because r prime and r are different. R prime is after bending and r is before bending. R is the original radius of curvature before bending, but r prime becomes a new radius of curvature when moment is applied. So, the change in radius of curvature multiplied by my E will give me my stress by strain ratio, which is different from conventional theory of flexure, right. So, now we have certain assumptions in curved beams also. Let us see what are the assumptions we make. in curved beams. They are similar to straight beams. Let us see what are these assumptions. The first one is every cross section of the beam, we can say, to be very specific, of the curved beam remains plane and perpendicular to the centroidal axis. This happens before and after moment is applied. If you take any cross section of the curved beam normal to its centroidal axis, let us say I have a curved beam, I take any section and this section is the central axis, and if section is cut normal and this section remains plane before and after bending. Bending in sense when moment is applied. The moment may be applied by increasing the radius of curvature. So, the cross section does not bend, it remains plane. Okay, it remains plane. That is the first assumption we have. So, to satisfy this condition, one should agree on the following: net force acting on any cross section of the curved beam should be what? Should be what? Okay, good. Should be 0, because plane sections remains plane before and after bending is applied. If you do not have this condition satisfied, if this is not satisfied, then the cross section would, what will happen to the cross section? We assume it is plane, but what will happen to it? It will warp, it will twist. Okay. So, we assume that twisting does not happen, because if twisting happens, this equation is not applicable. Okay. It does not warp, it does not twist. So, mathematically sigma dA over the whole area should remain 0, call equation number 7. I think 6 we have already done. Yeah, 6 we already done. So, we go for 7. So, now I substitute equation 6 in equation 7. Equation 6 is here. Okay. This is equation 6. I substitute back in 7. So, I write integral Ey 1 by r prime minus 1 by r of dA is set to 0 for the whole area. Now, I can take the constants out of the integration, saying that E times of 1 by r prime minus 1 by r integral y dA is 0. Okay, let me rub this and simply say equal to over area A. So, friends, I call this equation number 8. In equation 8, either this should be equal to 0 or this should be equal to 0, then only this condition is satisfied, is it not? Now, we all know this amount cannot be 0, because E is not 0, that is Young's modulus of the material. and radius of curvature difference cannot be 0, it is a number, it is an absolute number. So, this product can never become 0. If at all this equation should be satisfied, the only condition is this should be 0. Okay. So, we am applying that since E times of 1 by r prime minus 1 by r cannot be 0, it is an absolute quantity, cannot be 0, integral y dA over A need to be 0. Equation number 9. What does it imply? This condition implies that the geometric axis coincides with the neutral axis. Okay. That is the meaning of this statement 9. This can happen only when y is 0. A cannot be 0 because A has got a definite quantity. What is y? Y is the distance of any fiber from the centroidal axis. When I say the first moment of area is 0, that can happen only when the geometric axis and the neutral axis coincides. Okay. Having said this, as the curved beam is in equilibrium under the applied external moment, m, one can also note that sigma dA over A is m, equation 10, because external moment is applied. Now, substituting for stress from equation 6, we get, let us see what is equation 6. Please turn on your notes and see what is equation 6 and what is stress value. Now, I am substituting, I am writing it here. Okay. E times of 1 by r prime minus 1 by r integral y square dA of A should be m. Okay. Friends, as per the mechanics basics, what is second moment of area? Can I say second moment of area is a moment of inertia about the central axis? If I say that, then we can say since second moment of area about the central axis moment of inertia, hence E times of 1 by r prime minus 1 by r of I is m. So, we get a classical equation m by I is E times of 1 by r prime minus 1 by r, which is also equal to stress by y, and that is the classical equation of derivation for curved beams. Okay. So, friends, in this class we learnt about derivation of curved beams with small initial curvature. We designated how a curved beam can be classified. We fundamentally derived the equation of bending, which is stress by y, is m by I, which is E times of 1 by r prime minus 1 by r as the equation of bending for curved beams with small initial curvature. Okay. So, what is small initial curvature? Small initial curvature is the initial radius of curvature by the depth of section is greater than 10, where r is the radius of curvature, initial radius of curvature, and h is the depth of section. If this condition is satisfied, then we can say it is beam with small initial curvature, and the above equation is useful to compute the stress in the cross section because of any moment applied on the cross section. If you know the moment of inertia of the section, and if you know the material property, and if you know the change in curvature because of application of M. Okay. So, one can compute the bending stress at any point in the cross section you want if the beam is subjected to or classified as beam with small initial curvature. Should I have any doubts or any questions, please post your doubts to discussion forum in SwayamPrabha. Instructors will be also getting back to you with clarification, but I would urge you to go through the derivation clearly. Please reinforce your capacity of learning by understanding, not by memorizing the equations. Please do not memorize them, it will not stand for a long time. So, try to understand them, rederive them again. I have done step by step, please also draw the figures on your own, so that you remember the nomenclature very carefully, and you will remember about 10 steps to get this equation which is on the screen now. Thank you. Namaste.